we have seen the series formula for ln of x, that is the Laguerre polynomial of degree n, in the last lecture. Now, after knowing the series formula, today we are going to know about the differential formula for ln of x. Actually, this differential formula for ln of x is also known as Rodrigues formula for Laguerre polynomial. So first of all, we will see what is the Laguerre formula for ln of x, and then we will prove it. See here, I have mentioned the Rodrigues formula or differential formula for ln of x. This is defined in this way. Ln of x is equal to e raised to the power x dn dxn xn e to the power minus x. It means you have to differentiate the function x raised to the power n e to the power minus x n times, and then you should multiply it by ex. Then you will get ln of x. Actually, this formula is known as Rodrigues formula for ln of x. Now, our aim is to first of all prove this formula, and then using this formula we will see some of the values of ln of x. Actually, this formula can be proved starting with the generating function for ln of x. And in this regard, you must remember this generating function expression for ln of x. Actually, the generating function for ln of x is defined in this way. If we consider that g of xt is the generating function for ln of x, then it is defined as e raised to the power minus xt over 1 minus t equal to 1 minus t summation over n 0 to infinity ln of x over n factorial t raised to the power n. In fact, you can write this generating function expression for ln of x in this way. Let us multiply by this 1 minus t to the LHS, 1 minus t raised to the power minus 1 to the LHS. Then we will get 1 minus t raised to the power minus 1 e raised to the power 1 minus 1 over t times x. In fact, this minus xt over 1 minus t, you may write in this way: 1 minus 1 by 1 minus t times x. You may verify it. And then LHS will be summation n 0 to infinity ln of x over n factorial t raised to the power n. Now, this factor, exponential factor, you may break into two parts. This is e raised to the power x times e raised to the power minus x over 1 minus t, and RHS remains at ease. Now, let us differentiate this equation 1 n times by Leibniz theorem for successive differentiation, and then you can see what will be our result. So, let us differentiate it with respect to t n times. Differentiating 1 with respect to t n times by Leibniz theorem for successive differentiation. When you will differentiate this equation 1 n times by Leibniz theorem for successive differentiation with respect to t, then you will get we have, you can see e raised to the power x is not a function of t, so we take it outside of the differential operator. So this will be e raised to the power x and dn dxn 1 minus t raised to the power minus 1 times e raised to the power minus x over 1 minus t. Now see the RHS. If you will in fact expand this function, you can see the first term will be what? This will be L0 of x. First of all, we should write the operator here. This will be dn, sorry, here will be dt, not x, because we are differentiating with respect to t. So dn dtn, and now we will simplify this term, summation term. You will see when we will take n equal to 0, then this will be L0 of x, L0 of x. Sorry, there is no need to expand this series. I am going to directly differentiate it using the Leibniz theorem. So this will be dn dtn summation n equal to 0 to infinity ln of x over n factorial t raised to the power n. Now let us simplify the RHS of this equation. You can see, since you know, if we will differentiate any function containing power n n times, then the terms containing the power up to power n minus 1 will vanish. For example, you can see that if we consider there is a function x square and we differentiate it, let us say 3 times, and the function is, let us say, x cube, then you can see d3 dx cube x cube will be what? First of all, this will be d2 dx square 3x square, and then this will be d dx 6x, and then this will be 6. So if we will now differentiate it again, then the result will be 0 because the final term is constant. So from this you can say that all the terms up to the term containing t raised to the power n minus 1 will vanish after differentiation n times. So what will be our result? You can see here. This was just for the illustration, so I am erasing it. Now you can see, as I have told you, all the terms up to the term containing t raised to the power n minus 1 will vanish after differentiation n times. So our result will be what? You can see this will be ln of x plus ln plus 1 of x into t and plus so on. This will be our result. Now we will see what will be the values of this expression for different values of n. So for this, let us consider this equation. This is equation number 2, and now see what will be the value of this term when n is equal to 1. So let us consider. Now you can see d dt 1 minus t raised to the power minus 1 e raised to the power minus x over 1 minus t. What will be this? First of all, we will differentiate it directly by the rule of differentiation of product of two functions. You can see here there is a product of two functions. The first function is 1 minus t raised to the power minus 1, and the second function is e raised to the power minus x over 1 minus t. So following the rule for the differentiation of product of two functions, you may differentiate it, and you can see it. You can see what will be this result. So let us take 1 minus t raised to the power minus 1 at each, and then we will differentiate the other factor e raised to the power minus x by 1 minus t. So what will be its dc with respect to t? You can see this will be e raised to the power minus x over 1 minus t, and then we will differentiate minus x over 1 minus t. This is just a function of function, and then this will be into minus x times minus 1 over 1 minus t whole square times minus 1. This is the term when we take 1 minus t raised to the power minus 1 as at each and differentiate e raised to the power minus x by 1 minus t. Now we will differentiate the first factor and take the second factor at each. So this will be e raised to the power minus x by 1 minus t times differentiation of 1 minus t raised to the power minus 1 will be what? You can see this will be minus 1 over 1 minus t whole square. Then we will differentiate 1 minus t, and dc of 1 minus t will be simply equal to minus 1. So this is the result after differentiating this function 1 minus t raised to the power minus 1 times e raised to the power minus x over 1 minus t with respect to t. Now let us simplify the RHS a little bit. You can see d dt 1 minus t raised to the power minus 1 times e raised to the power minus x over 1 minus t. What will be this? See the RHS. You can take e raised to the power minus x over 1 minus t whole square as a common factor. Then the remaining terms will be 1 minus x over 1 minus t. You can see it. And so now let us simplify the RHS by taking the LCM. You can see this will be e raised to the power minus x over 1 minus t whole square, and this will be 1 minus t minus x over 1 minus t. So you can write that this d dt of 1 minus t raised to the power minus 1 e raised to the power minus x over 1 minus t is equal to what? You can see this will be e raised to the power minus x times 1 minus x minus t and over 1 minus t raised to the power 3. So this is the result. Now we will see what will be the value of this expression when t tends to 0. So you can see. So limit t tending towards 0 d dt 1 minus t raised to the power minus 1 times e raised to the power minus x over 1 minus t. What will be this? You can see this will be limit t tending towards 0 1 minus x minus t times e raised to the power minus x over 1 minus t raised to the power 3. And so you can see when we will put t equal to 0, then this expression will be simply 1 minus x times e raised to the power minus x over 1, because t is now 0. In fact, this expression in RHS can be written as d dx x times e raised to the power minus. You may check it. When you will differentiate this x times e raised to the power minus x with respect to x, you will get 1 minus x times e to the power minus x. You can easily check it. Now in the similar manner, you can find the limiting value of d2 over dt square 1 minus t raised to the power minus 1 times e raised to the power minus x by 1 minus t when t tends to 0. In the similar manner, you can say what will be your result. By induction, you can say. So similarly, we may write limit t tends to 0 d2 dt square 1 minus t raised to the power minus 1 times e raised to the power minus x over 1 minus t. By induction, you can say what will be the result. See here, when there is operator d dt, then we get d dx x times e to the power minus x. So when the operator will be d2 by dt square, then here will be actually d2 dx square x square e to the power minus x. By induction, we can easily say it. So this will be d2 dx square x square e raised to the power minus x. So in general, you can write the expression for n. So thus in general, we may write limit t tends to 0 dn dtn 1 minus t raised to the power minus 1 e raised to the power minus x over 1 minus t will be what? You can easily say this will be simply dn dxn x raised to the power n e to the power minus x, and say this is equation 3. I have already assumed the equation number 2, so say this is equation 3. Now we will impose the limiting condition, that is t tends to 0, on equation 1 which we have obtained earlier. See here, this is equation 1, and now we are going to impose the limiting condition t tends to 0 on this equation 1. First of all, see here, when you will impose this condition on this equation, when t tends to 0, what will be your result? You can see easily. In fact, this is not on equation 1. We will impose this condition on equation number 2, not on 1. So see here. So imposing the limiting condition t tends to 0 on equation 2. What will be our result? You can see this will be e raised to the power x limit t tends to 0 dn dtn 1 minus t raised to the power minus 1 times e raised to the power minus x over 1 minus t. And see this equation number 2 here. You can see LHS is this much, and I have imposed the condition, limiting condition, t tends to 0 on it, and see the RHS. When you will impose the limiting condition t tends to 0, then except ln of x, all other term will contain t. As you can see, this n plus 1th term contain t, n plus 2th term will contain t square, n plus 3th term will contain t cube, and so on. So when we will take t equal to 0, then all these higher order terms containing ln plus 1, ln plus 2, ln plus 3 will vanish. And only after imposing this limiting condition t tends to 0 in RHS, ln of x will remain non-zero. That is, only the first term will remain non-zero. So after imposing this limiting condition on this equation 2, the RHS will be simply ln of x. So this is ln of x. Now say this is equation number 4. Now you can see from this equation which we have obtained here, this is the equation 3, and this equation 3 says that limit t tends to 0 dn dtn operated on this factor is equal to this much. So when we will use this equation 3 in this equation 4, then LHS may be replaced by dn dxn x raised to the power n e to the power minus x times ex. So from equation 3 and 4, what you will get? See here, in equation 4 there is e raised to the power x, and instead of this limiting term from equation 3, we can write this will be dn dxn x raised to the power n e to the power minus x, and this is equal to ln of x. So you can see what we have got here. You can easily write that ln of x is equal to e to the power x dn dxn x raised to the power n e raised to the power minus x. And this is the differentiation formula for ln of x, which is also known as Rodrigues formula. So this is your Rodrigues formula. So you have seen how easily we can obtain this formula by simple mathematical calculation. Now, after getting the differentiation formula for ln of x, let us try to find some of the values of ln of x for different values of n. So let us find it. So take first of all n equal to 0. When you will take n equal to 0, then ln of x will be L0 of x. And what will be this? You can see this is e raised to the power x d0 dx0 x raised to the power 0 e to the power minus x. And you know, when you write the operator d0 dx0, what does it mean? It is simply 1. It means we are not going to differentiate. No differential operator is operated on this. So this is simply e raised to the power x times e raised to the power minus x, and this will be simply 1. And therefore you can say L0 of x is equal to 1. You can see this formula is very easy to use to find the value of ln of x. Now let us take n equal to 1. In this condition, our Laguerre polynomial will be L1 of x. So in the defining equation in RHS, we will take simply n equal to 1. So this expression will be ex d dx x e to the power minus x. You can see I have taken n equal to 1. And now see here. Now differentiate it. As there is a product of two functions, so apply the rule of differentiation of product of two functions here, and you can see what will be your result. This will be, in fact, e raised to the power minus x times 1, and now plus 1 plus x plus x. Now we will differentiate e to the power minus x. This will be simply minus e to the power minus x. And so you can see this is e raised to the power x times e raised to the power minus x and minus x times e raised to the power minus x. And so when you will multiply by this factor e raised to the power x to the terms inside the bracket, this will be 1 minus x simply. So L1 of x you can see we got 1 minus x. Now we will take n equal to 2. So when n is equal to 2, then we will find L2 of x applying the same formula. You can see here n is 2, so RHS will be e raised to the power x d2 dx square and x square e to the power minus x. Now this is e raised to the power x d dx. This is d dx x square e to the power minus x. Now simplify it. This is e raised to the power x d dx. Now we will differentiate this product x square times e to the power minus x. So dc of x square will be 2x and times e to the power minus x, then plus. Now we will take x square at each and differentiate this e to the power minus x with respect to x, and this will be minus e raised to the power minus x. And so you can see this is e raised to the power x d dx, and this is 2x e raised to the power minus x and minus x square e raised to the power minus x. Now we will differentiate the terms inside the square bracket, and you can see this is e raised to the power x. Here there will be 2. dc of x will be 1. So 1 times e raised to the power minus x and plus. Now we will take x at each, and dc of e to the power minus x will be minus e to the power minus x, and now minus. Now we will differentiate x square e to the power minus x. So you can see what will be our result. In fact, this will be 2x times e to the power minus x and plus. Now this is x square times minus e to the power minus x. So see here, after simplification what will be our result, you can easily see here. So L2 of x, this will be e raised to the power x times 2e to the power minus x and minus 2x e raised to the power minus x and minus 2x e raised to the power minus x and plus x square e raised to the power minus x. And after multiplying by this ex to the terms inside the square bracket, you can see we will get 2 minus 2x minus 2x and plus x square. Therefore, you can say L2 of x will be what? This will be x square minus 4x plus 2. So this is L2 of x. And in fact, in similar manner, you can calculate L3 of x, L4 of x, and so on yourself. So you have seen the Rodrigues formula or differentiation formula for ln of x in this lecture, and you have also feel how it is easy to calculate the Laguerre polynomial of different degree by using this formula. So this formula is very useful, and in physical problem you always use such a formula.